Hello, this is Praveen. Today's topic is radiographic testing. Now I am going to present the utmost topics in radiographic testing. Radiography testing is one of the non-destructive testing process. So before going to radiographic testing, we should know what is non-destructive testing process. When we are finding defects in a material without causing any actual damage to that particular material, then we call it as non-destructive testing. So coming to radiographic testing, when we are using rays like X-rays or gamma rays, then we call it as radiography testing. In radiographic testing, rays like X-rays and gamma rays are used to examine the internal structure of manufactured components to identify the defects or flaws. Now let us see the history of radiography testing. Back in November of 1895, German physics professor Wilhelm Conrad Röntgen made an unexpected discovery that would transform science and the medical field forever. So he is referred to as the father of diagnostic radiography.
During his period, Röntgen was investigating cathode rays using a fluorescent screen painted with barium platinocyanide. He wrapped the Crookes tube in a black cardboard. By using that, he shielded the fluorescent glow. Then he noticed a faint green glow from the screen, which is 1 meter away from the screen. Now Röntgen realized some invisible rays coming from the tube. The rays were passing through the cardboard to make the screen glow, and they were passing through an opaque object to affect the film which is placed behind it.
While working on an experiment with electric current, Röntgen noticed mysterious light streaming on the screen. When he put his hand behind the light on the dark screen, he was able to see the bones of his hand. Röntgen called the strange discovery as X-rays, and in December of that same year, he exposed photographic plates to the rays and recorded the first X-ray image. The first X-ray image was his wife's hand. Now let us see the principle of radiographic testing. So the principle of the radiographic testing is that when we pass an radiation through any object, the radiation will be absorbed by that particular object. The exposure of the film will be affected if there are any variations in thickness of that particular material or density of the material due to defects in that particular object. Here, the flaws in that particular material will be identified by the darker areas in that film. Now let us discuss the radiation passing through an object with different thickness. Here the penetrating power of the radiation will be changed with respect to the different kinds of material. Here in this picture you can see the radiation is passing through a material which is having different thickness, and it also has a flaw in it. In these types, the defect will be identified by using the film darkness. The film darkness is created only because there is a local difference in the radiation absorption. So we can understand that the film darkness is due to the local difference. Next is important things to keep in mind. Properties of a penetrating radiation. One of the main properties of the radiations is that they only travel in a straight line. And another property is when we pass radiation through any certain object, the object will absorb that particular radiation. Here, the absorption of the radiation depends upon the factors like thickness of the observer, physical characteristics of the observer, and wavelength or photon energy of the radiation. Here, photographic emulsion is used for the detection of penetrating radiations. So next is important things to keep in mind when viewing a radiographic image. First, thickness, position and size cannot be determined. When we are inspecting a radiographic testing material, we can identify whether the material contains defect or not, but we cannot find the thickness, position and size of that particular type of defect in that particular type of material. Here we have to keep in mind that a radiograph is a two-dimensional image of a three-dimensional object. So next point is that defects will only appear as two-dimensional image. When we are inspecting a material by using radiographic testing, we can only get a two-dimensional image of that defect. So in radiographic testing, we can find only whether the material contains the defect or not, but we cannot find the position, size and orientation of defects in that particular material. Next, we can move to the electromagnetic radiation. Let us see what is electromagnetic radiation. Electromagnetic radiation is a form of energy. It is created from the electric field. The waves of the electromagnetic field is referred to as the electromagnetic radiations. Electromagnetic radiation is of different forms like radio waves, microwaves, X-rays and gamma rays. Sun is also a form of electromagnetic radiation. The visible light from the sun is a small portion of the electromagnetic spectrum, which contains a broad range of electromagnetic wavelengths. Now let us see the sources for radiographic testing. So radiographic sources. There are two most commonly used sources for radiation. They are X-ray generators and gamma ray sources. Here, when we are using X-rays, then the method is called as X-ray radiography, and when we are using gamma rays, then the method will be called as gamma ray radiography. Here we know that X-rays are generated electrically, but it should be noted that gamma rays are generated by the decay of unstable atoms. Now let us see the detailed explanation of X-ray radiography and gamma ray radiography. First is X-ray radiography. When we are using X-rays to detect flaws in any material, then the method will be called as X-ray radiography. In X-ray radiography, two-dimensional pictures of the defects will be produced. Now let us see the production of X-rays. For the production of X-rays, we need to have the following requirements. Number one is a vacuum. Number two is a source of electrons. Number three is target, and number four is a high potential difference between the electron source and the target. Here, the anode is considered as the target where electrons are going to hit. Now let us see the detailed explanation of the production of X-rays.
First is X-ray tube. X-ray tube is the part where X-rays are being produced. In X-ray tube, the electrical input power is converted into X-rays. High voltage supply. The main source of the X-ray is electrons. So to produce higher energy electrons, we have to give higher voltage. Lead shielding. We know that X-rays are emitted in the X-ray tube in every direction. So for protection purpose, we have to shield the X-ray tube by using lead.
Here, the unnecessary exposure of X-rays will be blocked by using lead shielding.
Vacuum chamber. In X-ray tube, the electron should be accelerated with maximum efficiency. So to gain maximum efficiency, vacuum is created in the X-ray tube. Cathode filament. Cathode filament is the source of electrons. Electrons will be expelled from the cathode filament. Here we have to focus the electron beam on the focal spot of the anode. Anode target. We have to convert the electrons into X-rays. Here the process is achieved by using the anode target. It should be noted that most X-ray tube anodes are made of tungsten because of its high melting point. Filter. We know that X-rays with low energy will not be useful. So here we are using filter to remove the low energy X-rays.
Now let me explain each and every part in detail. Number 1 is cathode filament. The purpose of the cathode filament is to produce electrons. Here we have to produce higher energy electrons, so high voltage supply will be passed. When we are giving a higher voltage, more amount of heat will be produced. So to withstand a higher amount of heat, we have to use a filament with high melting point. Here the electrons will be expelled from the cathode filament when it is highly heated by power supply. This process is called thermoionic emission. Here the amount of X-rays produced per unit time is directly proportional to the amount of electrons produced per unit time.
Number 2 is high voltage field. The purpose of the high voltage field is to accelerate electrons. Here the positive terminal of the voltage supply is connected to the anode filament and the negative terminal is connected to the cathode filament. High electric field is created in the cathode filament due to the high voltage supply. By using the electric field, we can accelerate the electrons towards the anode filament. Number 3 is vacuum chamber. The main purpose of the vacuum chamber is free flow of electrons, because when vacuum is created, obstructions will be removed, so electrons can flow easily. Now let us see what happens when electrons are made to flow through chambers filled with gas. Here the electrons are made to flow through the nitrogen atom. The mass of the nitrogen atom will be greater than the mass of the electrons. So you can observe that the electrons are scattered away in all directions.
Due to the absence of vacuum, the electrons will be scattered away from the target. Now let us see the path of the electrons after evacuating the chamber. Due to the absence of obstructions, you can observe that the electrons will reach the anode target with high kinetic energy. Number 4 is anode target. The purpose of the anode target is to convert the electrons' kinetic energy into X-rays. Here, the incoming electrons from cathode will collide with the anode target. So during collision, the acceleration of the electrons will be reduced. And here the kinetic energy of the electrons is converted to X-rays and heat.
In this particular type of X-ray tube, the anode target is rotated to distribute the heat all over the surface of the anode. Here you can see a material which is placed behind the stator. The material will be useful for additional cooling purpose. Here the X-ray spectrum will be altered with respect to the material we are using for the anode target. We can use different materials for anode target like tungsten, molybdenum and silver, etc.
Number 5 is lead shielding. We are using lead shielding because many electrons will be scattered out from the target. So lead shielding will absorb those electrons. There are the possibilities of scattering of electrons from the air molecules which is present inside the chamber and by the glass molecules. So the scattered electrons and X-rays will be more harmful for operators. That's why we are using lead shielding for the protection purpose. When we are using lead shielding, the radiation will be absorbed by the lead shielding. Lead is used for the shielding purpose because it has high density. Hence, it would have high density of electrons.
Number 6 is filter. Here, the purpose of the filter is to absorb the low energy photons. We know that for producing X-rays, higher energy photons are required. During the X-ray production process, lower energy photons are also produced. So, to remove the lower energy photons, filter is used. The filter which we have used here is aluminum sheet. In this video, you can observe the reaction of that filter with respect to the higher energy photons and lower energy photons. And also you can see the graph of filtered and unfiltered spectrum. And finally the X-ray tube. The combination of each and every parts which we have discussed now are combinedly called as X-ray tube. And the purpose of the X-ray tube is like cathode filament produces electrons, high voltage supply accelerates electrons, vacuum chamber removes obstructions, the anode target converts kinetic energy of electrons into X-rays, lead shielding absorbs radiations, and aluminum filter absorbs lower energy photons.
So, as we seen in the video, we know that the first step for X-ray production is requirement of free electrons. It should be noted that the free electrons should be present in the evacuated environment. The need for the evacuated environment is to allow electrical conduction between the electrodes which is present inside the X-ray tube. We know that the electrons will be released out from the cathode filament. Now the anode filament, which is positively charged, will attract the electrons which is coming from the cathode filament. When these fast moving electrons are collided with the target, then the kinetic energy of the electrons is converted into different forms of energy like heat and X-rays. Here it should be noted that the target material should have high melting point to overcome the heat. Finally, it is clear that 99% of kinetic energy of the electrons is converted into heat and only a small amount of energy is converted into X-rays. These are all about the production of X-rays. Now let us see the production of gamma rays. Here the production of gamma rays is different from the production of X-rays. We have to keep in mind that gamma rays are produced during the disintegration of radioactive atomic nuclei and the decay of certain subatomic particles. Now let us see the natural production of gamma rays.
Gamma rays have the smallest wavelengths and most energy of any wave in the electromagnetic spectrum. They are produced by the hottest and most energetic particles in the universe, such as neutron stars and regions around black holes. Here you can see the production of ions by the collision of two protons. Then after the decay of that ion, gamma rays has been created.
Now let us see how the gamma rays are produced artificially. Artificially, gamma rays are stored in a machine which is called gamma cameras. It is also called scintillation cameras or Anger cameras. The Anger cameras are the major imaging machines which are currently in use. Like X-rays, gamma rays are also produce planar images. They are also similar to single photon emission computed tomography. Now let us see a radiographic testing of a material by using gamma rays. Gamma radiation can be used to identify the cracks in welding and pipes. By using this testing, we can give an early warning of failure. This process is also used in aeroplane safety checks. The gamma ray works in a method which is similar to the X-rays. Gamma rays are also produces dark spots when there is a fault. Now let us see an animated video of gamma ray testing.
In this video, you can see the radiography testing of weld works. Radiography technique is used to determine flaws in ferrous, non-ferrous metals and other materials. This is also used to test the weld works. Here, the components are exposed to shorter wavelength radiation in the form of X-rays, where wavelength is 0.001 into 10 power minus 8 cm to about 40 into 10 power minus 8 cm. Gamma rays, whose wavelength is about 0.005 into 10 power minus 8 cm to 3 into 10 power minus 8 cm from a suitable source such as an X-ray tube or cobalt-60 can also be used instead of X-rays. Gamma rays, which are produced by radioisotopes such as cobalt-60, can penetrate through specimen and can inspect better thickness than X-rays. Here, the specimen is tested by placing between the source of radiation and film. Here, the film is used as a recording medium. Both sides of the film base are covered by protective coating and emulsion coating. Here, the base is made of polyester and provide transparent medium. The emulsion is the suspension of silver and salts in gelatin. The emulsion coating is used to increase the quantity of radiation absorbed, and externally we have to give protection coating to safeguard the film. Large radiations are passed in defecting areas and the film appears to be darker. The main advantage of radiography test is that it is very much suitable for identifying flaws in thin section, and it is suitable for any type of material. The disadvantage of radiography test is that it is not suitable for detecting defects in thick sections and also in surface of the specimen. And another disadvantage is that it cannot indicate the depth of the defect below the surface. And one of the major disadvantages of radiography test is it causes health hazards. Thus, these are all about radiography testing.
Now let us see the applications of radiography testing. Radiography testing is used in various sectors like aerospace industries, automobile industries, manufacturing industries, medical devices, military, defense, and for medical use, etc. These are some of the applications of radiography testing. Now let us see the radiography testing for the pipe. Radiography testing utilizes ionizing radiation to achieve an image of an object on several different viewing mediums. This may be gamma rays or, as in this case, X-rays. Here the examiner marks the belt to be inspected with a measuring tape. This will be visible on the X-ray, thus he will know how to determine the exact location of possible irregularities. Then the film is mounted on the object and the X-ray tube is set up carefully. Then the examiner leaves the area, closes the lead door and operates the device remotely. So this way he can avoid coming into contact with the radiation. He adjusts the voltage, current and duration depending on the investigative material and he starts the irradiation.
Now let us see the animated video of X-ray inspection. The X-rays go through the material and generate a radiographic image on the film or imaging plate once processed. Now the experienced eye of the examiner interprets the image and he can now determine the quality of the inspected object and if it meets the standards.
Now let us see the advantages of radiographic testing. First advantage is that we can inspect a material with varying density. Here in this picture you can see a material with various densities. And here the darker spots are produced on the film with respect to the density of the given material in the picture. Another advantage is that assembled components can also be inspected. Minimal surface penetration is required for radiographic testing. And one of the main advantages of radiographic testing is that we can determine the crack growth in advance. By using the radiographic testing, the surface and subsurface defects can be identified. And the main advantage of radiographic testing is that the permanent record of the inspection can be obtained. Now let us see the limitations of radiographic testing. Number one is radiographic testing should be done in a closed area because of hazardous radiations. So safety perimeter is very much required in radiographic testing. Number two is the equipment used for radiographic testing is highly expensive. Number three is radiographic testing process is comparatively a slow inspection process when compared to the other testing process. Fourth limitation is that it is sensitive to flaw orientation. Number 5 is we cannot determine the depth and position of the defects in the material which is given for the inspection process. And the final limitation is that the testing material requires two-sided access. Now I have given the overall presentation of the radiographic testing. So if you have any doubts, you can mention below in the comment section. And thank you.